All right, welcome back to 1220. So I want you to start today by jogging your memory. How would you attack a problem like this if it popped up on your screen on Friday when you were taking the exam? All right, so feel free to also pull up the exam supplemental information, so the sheet of equations that you'll have on Friday, because you'll need one of those to solve this if you don't have it memorized, which is fine. You just need to know which one to grab based on the information given. Okay, so take a second, find that equation either on the SI or from your notes from Tuesday, and solve, in this case, for K. It's also a good thing to remember that the rate constant, we're asking for K. All right. So do feel free to turn to the person next to you, see what equation they pulled. How are they attacking this problem? All right, let's look at this together. There's actually two ways that you could go about this. One of them, I'm gonna do the one that came to my mind first, okay? And that was because I saw second order, okay? So as soon as I see second order, I know that's bringing up a specific set of equations. I need a rate law that is second order with respect to its reactant, okay? And then I look at the information that I'm given. I have time explicitly. As soon as I see time, that tells me I need an integrated rate law. So I want this second order integrated rate law. That's, of course, not labeled as such on your exam sheet, but it's there. So I'd go and I'd pull it out and say 1 over AT. So that is the concentration at time t equals the rate constant times time, how much has passed, plus 1 over the initial concentration. All right, give me a thumbs up if that was the equation you pulled. Good. All right, and now it's just plugging in and identifying the right, putting the right things in the right places. All right, so AT, what do we have at 225 seconds? All right, it became, I don't love the way I wrote this, but anyways, at 225 seconds, a 1.5 molar solution of A becomes, or reacted to become, a 0.75 molar solution. So that's my AT, okay? This was my A naught. That's how much I had to begin with, and that's how much time it took for that to happen. So I could have 1 over, and I'm going to just start plugging these in. All right, so I'm going to go through and I'm going to solve out, and I wound up getting, I'm going to subtract this 1 over 1.5 molar from both sides. I got 0.667 inverse molar equals K times 225 seconds. Solve out for K, and I got 0.00296 over molar seconds. Yes? Good? Okay. There's another way you could have gone about this, which maybe wasn't as obvious, and it doesn't matter. What's special about this 225 seconds? Anybody recognize that as a specific important time point? What percentage of A have we lost? The half-life. We have lost half of it. I had 1.5, I waited, and I have 0.75. That's 50%. So 225 seconds is my T sub 1/2. So I could also have pulled out the second order half-life equation, which is T 1/2 equals 1 over A naught times K. And I know that T 1/2. So in this case, I would be plugging in T 1/2 and A naught and solving out for K. And you'd get the same answer. So I'd rearrange this and say, oh, well, K just equals 1 over A naught times T sub 1/2. And you'd get that same K value. Okay? So either way would have worked. And I just wanted to remind you that half-life was a thing, so I picked the time point when half of it had disappeared. Questions on that? Okay. Then we are going to wrap up our last little bit on 14.5, which was about the Arrhenius equation. All right. So you turn your mouse on and you proceed forward. All right, this is where we left off on Thursday. This relationship, as we increase the temperature of a reaction, the reason that speeds up a reaction is because temperature increases our rate constant. And it's not a linear relationship, it's exponential. So every time we increase temperature, we're going to see a fairly significant jump in K. All right, so that's the exponential part of this. There are two fundamental, microscopic reasons for why that's true, right? One is that if you're moving faster, as you would be if you were heated up, okay, you're just going to collide more with each other, okay? You're moving faster, more collisions are happening. Collisions are the first step to starting a reaction. So more collisions, more likely that this is going to happen, faster rate, okay? That's one reason. The other is that when you do hit somebody else, when two reactants hit each other, they need enough energy to get over our energy barrier, the activation energy, all right? This hill right here. They need enough energy to get over that. As you increase the temperature, what you're doing is increasing the kinetic energy of your particles. So turn up the temperature, you are giving them more energy, which means they're more likely to have enough to get over that barrier. Okay? That's the primary reason temperature makes things go faster. Okay, that's second point here. They have more kinetic energy, which means they're more likely to have enough energy to get over that hill. All right? So Arrhenius described this relationship with an actual equation. All right, so we defined all of those variables. I have that written out here. K is our rate constant, and it's equal to A, which is our frequency factor. Okay? That is where we contain information about the collision frequency, the orientation factor. So how can we just have this reactant hit that reactant and it doesn't matter? Or are we looking at maybe this reactant and it's got to hit right here? Only that part of this larger molecule. It can't hit any other spot, right? And so how likely is it that we're going to hit with the right orientation? That gets folded into A, as well as some physical state information. It's a catch-all term, all right? And then we have EA, the activation energy, our gas constant, which is now in these units. Don't try and use the ones that are in atmosphere because you'll get the wrong answer. Make sure you're pulling the one with joule, all right, a unit of energy, and then temperature in Kelvin, all right? You get this equation as well on your sheet, all right? So a lot of times when you are in lab and you're actually doing kinetics experiments, the goal is to find what that EA is. Experimentally, what is this barrier? That is interesting and useful information for us. All right? And this is one of the only experimental ways to get at that distance. How high is that barrier? All right? And it's in there. I see it right there. Okay? I want to solve for it. So what we do is change the temperature, right? And then we measure new values of K. But no one likes working with e's, right? No one wants to work with an exponential equation, so we're going to do a little math to make this easier for ourselves. So we're going to take the natural log of both sides, because I want to get rid of this e right here. So I'll have the natural log of K, which is my rate constant, now equals the natural log of A times e to the negative EA RT, divided by RT. And I'm going to use one of my log rules, right? So the natural log of A times B equals the natural log of A plus the natural log of B. So I'm going to split out these two. All right? And then another rule. The natural log of e to the x, that just equals x. So this lets me drop out this term here, which is really what I was hoping to do. So the natural log of k equals the natural log of a minus ea over r times 1 over t. All right, and I did that on purpose. I wrote it like this because I want to separate out my 1 over t. Remember, temperature is the variable I'm changing. I can change temperature. That's easy. I put it in a water bath and I heat it up, right? And then I measure K. And so now we see ourselves in a similar situation. I'm going to bring us to the next slide, which has this same equation written out for us. Sort of similar to what we did in our integrated rate laws. If I graph, so the graph of the natural log of the rate constant versus 1 over t, that gives me a linear model, right? A linear relationship. ln of k is y. ln of a is b, our intercept, plus mx. And I'm going to graph 1 over t as my x, which means that my slope is negative EA divided by R. That's my slope, and this is my intercept. All right, so I went into lab. I did a bunch of different trials at different temperatures. I monitored their Ks. I have those now. And now I graph the natural log of K, my rate constants, against 1 over T. And I get a straight line. All right? That slope equals negative EA divided by R. So if you were given this equation, you say, hey, that straight line, I fit it, and I know that that's equal to 31.73 minus 19,615x. I could now ask you for these variables. Okay? So the slope, we'll pull that first, equals negative 19,615. If you look at the units, it's going to wind up being Kelvin, and that equals negative EA over R, right? I'm just pulling it straight from that equation. And again, I want to know what the activation energy is. That's a fundamental feature of this reaction. I want to know it. So I'm going to solve for it just by multiplying each side by negative R. All right, my negatives will cancel, so I'll have R, which is 8.314 joules per mole Kelvin, times 19,615 Kelvin. And that gave me, where are you? 163,000 joules per mole. All right, and this usually, and we'll give you one more. That's 100 there. And we usually will report this in kilojoules, so I'll make that final conversion and say my EA, my activation energy for this reaction was 163.1 kilojoules per mole. Okay. So if I give you the slope of this graph, I can get EA. That is important. I want to know how hard it is. That tells me something about how hard is it to break the bonds from the reactants over to the products. How hard is it to get up to that transition state? I get an actual energy number, which is very hard to get, but we can do it with this experimental approach. The other thing I asked for was A, what's our frequency factor? So I'm going to grab my intercept, and I know that my intercept equals the natural log of A. So if I want to solve out for that, I just need to bring both sides to the E. Okay? So A equals E to the 31.73, which is a large number. There's my A. So on the exam, we are going to give you graphs. Okay? In your first step, I would look at the axes and get yourself oriented. What are the axes? You're probably going to really have like a knee jerk and say, oh, there's a natural log. I'm looking at a first order integrated rate law. Then you say, no, I'm not, because it's not against time. It's against 1 over t, and it's not of concentration. It's of the rate constant. Okay? So get yourself oriented with the units and what we're actually looking at on a graph. All right, so this is one way to ask you about EA and A. The other way is to give you this 2-point, which you get this one as well. So you guys have this on your equation sheet. This is the 2-point Arrhenius. Okay, so notice here, I've dropped out A. Again, A is not usually what we're interested in. We want the activation energy. Okay, so I'm going to solve for the slope given 2 points. Basically, I say, hey, I know the rate constant at a temperature, and I know the rate constant at a second temperature. That's just saying, hey, you have 2 points, and knowing 2 points, you can determine what the slope is, right? There's only one line that connects those two, and it has a characteristic slope. That's what this equation does for us. In the next example problem, I have it set up where you're going to solve for EA, but there's no reason why I couldn't ask you for any of the other 4, right? There's just 5 variables. I'll give you 4. You tell me the last one, all right? So take a second, set this up for yourselves, or a minute. Take a breath. Okay. This is just a plug and chug question that feels overwhelming because of the structure of that equation. What is the activation energy for this reaction? You get 2 data points, 2 temperatures, and 2 rate constants. You know everything in this equation except for EA. The biggest mistakes you're going to make are calculator punch errors, using the wrong R, so make sure you grab the right R, that 8.314, and make sure you use temperature in Kelvin, so you're going to want to make sure to convert to Kelvin, and then make sure you are pairing your rate constant and temperature correctly. So I would start here and say, like, I'm going to call this 1, and I'm going to call this 2, just so that I don't screw up the placement of my K1 and K2 versus T2 and T1. Okay, get your last thought in. I'm going to plug in my numbers. All right? So again, this is plugging and chugging really carefully. All right? I like to write a 1 next to it so that I know where I'm putting things. I'm going to call this top cell my 1 trial and this one my 2nd trial. So I begin with the natural log of K1. And you can do it either way and you will get the right answer. But you just have to match your temperatures and Ks appropriately. I'm solving for EA. I'm going to put in the correct R value. I'm converting these to Kelvin. This is 462.9. This is 472.1. I'm grabbing T2 first. All right, so here's what I have. I'm going to just condense some of this, solve out. I'm getting the natural log of 0.48, okay? That equals EA, still have 8.314 there, joules per mole Kelvin, times, in this parentheses, I got negative 4.21 times 10 to the negative 5th. That's 1 over K. All right, I'm going to go through and I'm going to solve out for EA. I'm just dividing by this number and I'm going to multiply by R. The EA I got was 144,900 joules per mole, and it's likely we'll ask for it in kilojoules, so I'm going to divide that by 1,000. So my EA is 144.9 kilojoules per mole. A couple things about doing this and being like, hey, did I get that question right? EA is usually, let's really broadly, let's call it like 100 kilojoules per mole. All right, that's the order of magnitude. If you find yourself with an answer of like 10 to the minus 5 or 10 to the minus 20, good chance you've made a mistake somewhere. If you find yourself with a negative number, you have also made a mistake. It's got to be positive because you have to be going up and over. Okay, that's got to be a positive number going up. All right. If you did not get to the calculator punching, do it for yourself. Because this is like conceptually not that hard of a question. It is just putting in numbers and making sure that you punch them in correctly. Okay? All right, that's the last little bit about Arrhenius. This is where we are now. Let's take stock of what we've learned about kinetics. Okay? I've got a really solid amount of material I have to get through today. Otherwise, it's going to come at you on Thursday, and then it's going to be the day before the exam, and I don't like to do that. So give me your attention. We have differential rate laws, all right? That's what we solved for with our initial rate method, okay? How does the rate depend on our concentration, and can we get a value of K? All right? And then we said, hey, it would actually be really nice to relate concentration to time. That's the fundamental question of kinetics that we like to answer. How long will it take for this thing to react? How long will it take for me to make this? We need those integrated rate laws. And then lastly, we just did this, where we connected K to all these other variables. How do these things quantitatively change the speed of our reaction? That's this equation. We have EA and temperature, and then this collisional, this frequency factor in there. Okay? That's all packed in there. What we haven't done yet, we have made a lot of assumptions about this, where we just say, hey, that is just an up and over. And now we have to acknowledge that oftentimes it is not a simple up and over. There is a multi-step mechanism underlying that process. So the question in 14.6 is, what is the mechanism? All right? So let's talk about mechanisms. All right? So the reaction mechanism describes the actual steps. All right? Like, we do this first, and then you do that. It could just be that it was one step, and it's very simple, one over the top, but it's usually more than one. we want to break up this mechanism into elementary steps. Okay, elementary reactions. These are the things that I've been mostly drawing, where it goes, hey, we're going from here to here. This would be one elementary step. Okay? But most reactions don't do this. Most reactions are pretty complex, and we have to do multiple elementary reactions. So we're going to look and break down these reactions as like, hey, you're going to do this first, that first step, and then you're going to do another step. And we want, rather than looking at it as, oh, you're just going from here over to here, we need to look at those individual steps. Okay, that's the mechanism. All right, and I'm writing over my stuff. Just erase that for now. All right, so the equation that you all are used to seeing, the balanced net equation, tells you just where you start. What are the reactants and what are the products? And it can sometimes mask what's happening on the way there. So it doesn't tell you how we get there or what the steps are. And that's what we're going to answer now. All right, how do we get there? So here is an elementary reaction. We looked at this one. This is a first order reaction where methyl isonitrile converts to acetonitrile. So we're just flipping this bond here. And this is a single step. There is only one transition state. So the one peak. That tells me it's a single step. Okay? I'm just bopping over. All right? And that tells me that all I'm waiting for is one molecule to decide, hey, I'm going to flip this bond. Instead of having a CN here, I want that CC. All right? And it flips. Okay? I can write for an elementary reaction, the rate law can be written from an elementary reaction. What do I mean by that? Well, I mean like the stoichiometry. I can look at this and say if this is an elementary step, all I'm going to say is that the rate equals some rate constant times the concentration of my reactant. Okay, there's nothing else funky going on here. It's a single step. It's got to depend just on the concentration of that methyl isonitrile. Okay, so we can do that. Right. We want to talk, in addition, about the molecularity of these elementary steps. Okay, so if it's unimolecular, it's one reactant. So we just looked at a unimolecular reaction. If there are two reactants, it doesn't matter if they're the same reactant, but if there's two things that are coming together, that's bimolecular. And anything beyond that is called termolecular. Okay? And termolecular, I guess I'll save this point for the next slide. So here's a unimolecular, what we just considered, and it's an elementary step. And I get to write the rate law by just looking at this reaction and say, if that is an elementary reaction, I can write that the rate depends on just that concentration. If we are looking at a bimolecular reaction, this is ozone and NO, so O3 and NO. I am waiting in this transition state, I'm waiting for these two to hit each other. That is the mechanism. Ozone and NO, they come together and they hit and they form O2 and NO2. That's bimolecular, and my rate law will be dependent on the concentration of my two reactants. Because in that mechanism step, I am waiting for O3 and NO to hit each other. Okay? So that's what the rate should depend on. We're going to find that this rate law is telling us about the mechanism. How fast will it go? Well, what is the step that I'm waiting for? I need O3 to hit NO. Okay, and we see that off the graph here. So here's our molecularity in a bunch of different ways that we can conceive of it. We've got unimolecular, we're just waiting for A. Here are the elementary reactions that they might go with. Okay, so that I'm looking for A plus A or A plus B are two bimoleculars. And then we have our termoleculars. All right, where I'm waiting for A to hit itself, to hit two other A's, or A and B, or A, B, and C. And what we find when we actually go do experimental work on kinetics is that termolecular steps don't exist really, okay? That is a big ask, all right? So, remember how we thought about this? Let's say we're doing a gas phase reaction. And it's really, really, really unlikely in the gas phase because we are waiting for two molecules to hit in the right orientation just out in space. Now add in, we're going to also say for this reaction to happen, I need a third molecule to hit at the exact same time in the perfect orientation with enough energy. And that basically never happens. All right? So it is a big ask to have three things collide in space with the right orientation and the right amount of energy. And so they're rare, if they exist at all. If you find that it's termolecular in lab, it might just be that you haven't been able to figure out the underlying steps and that they're just going really fast. Okay? We find that termolecular steps are so slow that they're not feasible mechanisms. Okay, you can propose them, but it's unlikely that that's actually what's happening. So we want to write any feasible mechanism where the steps are only unimolecular and bimolecular. Those are reasonable. That's what we want to write. If we're going to write a good mechanism, they usually only include mechanisms with one molecule reacting or two molecules reacting in the steps. All right. So here is a multi-step mechanism, a reaction diagram. We want to label some things on here. Our reactants and products are, of course, where we're starting and ending. Any peak is our transition state. So we've got two transition states, which means that there are two elementary reactions. I would also call this a two-step process. All right? This point here is a new term that we need to acknowledge. That is an intermediate. All right? It is a local minima. All right? It's not the lowest point on the graph, but energy goes up on either side, meaning it's stable. In theory, I could trap that intermediate. Okay, I can't trap the transition state because on either side energy goes down. Nothing's going to sit there, but something could sit here, and I could, in theory, study that intermediate. Okay. The other thing I want to point out is that we want to write our activation energies for each step. So this is my first activation energy. The intermediate for the next step is now where I draw the start of my second activation energy, right? I'm going to stop there. It's like a layover. My intermediate, I'm there, I have that energy. How much energy do I need to get up and over that next bump? That's EA2. All right? So those are some definitions that we need as we actually go in and try to analyze a multi-step mechanism. All right? Oh, I forgot. We are not going to look at anything like this. But this is from a paper, okay, studying the energy diagram from reactants to products with this many steps. We are going to we'll max out at like 3 steps. You'll usually only see 2 steps. I just wanted to give you a flavor of what some people actually study, which gets really complex. All right? And now you can forget this image ever existed. All right. So let's do this for an actual reaction, okay? We are looking at NO2 and CO reacting to form NO and CO2. All right? Without any experimental data, you might assume that this is an elementary step, okay? That this is an elementary reaction. if you assume that, you would say, okay, I think the rate law should be K times NO2 times CO. You would be thinking, hey, for this thing to happen, all I'm doing is I'm waiting for an NO2 molecule to hit a CO molecule. And once they hit, the reaction proceeds. Okay? That's what that rate law would suggest. All right? And then, of course, you go into the lab, and you actually run the experiment, and you don't get that rate law. You get this rate law, that the rate equals K times NO2 squared. CO is not even in the rate law. You're like, how is that possible? When you see that the rate law, so when the rate law doesn't match what you would expect if the reaction were one elementary step, you can surmise or you can guess it must be a multi-step mechanism. All right? So because that is not what I would expect from that, if that was just, hey, I'm waiting for those two to hit, then it should depend on the concentration of CO. But instead I went into lab and found out it doesn't matter how much carbon monoxide I put in there. And I say, I must have a more complicated mechanism. And I got to figure it out. Okay? Okay. So somebody else, not you all, okay? Somebody else will look at that and suggest a mechanism, okay? They know that this is the rate law from experiment, and they say, I think this could be the mechanism. All right, so again, you do not need to create these mechanisms, but you need to be able to analyze them, okay? So we want to be able to look at that and say, hey, is that a reasonable multi-step mechanism? And there's a couple criteria that we will consider before we derive the rate law for it. So one, when you propose multi-step mechanisms, we still have to honor the overall chemistry that happens, right? So these two steps, they need to sum to my overall reaction. Okay, how do we do that? Well, we add up all of the reactants from step 1 and step 2, and then we add up all of the products from step 1 and step 2. We cancel anything that's on both sides, and we make sure it's our overall reaction. So let's do that. So I'm going to take step 1 reactants. I have 2 NO2. From step 2, I have NO3 and CO. Now my products, I've got NO3 plus NO plus NO2 plus CO2. Okay? So I've got all the things listed, and now I want to cancel anything that shows up on both sides. Well, NO3 is on both sides, so I cancel that. NO2 shows up, I've got 2 of them over here and 1 over here, so it cancels here, and one of those drops out. Okay? So I do have my overall reaction. NO2 plus CO does go to NO and CO2. That's what I wanted it to be. Right? So that's our first check. Does your mechanism actually accurately represent the chemistry? And this one does. All right? The other thing we want to ask ourselves is, are both of the steps uni or bimolecular? Right? Do we have any that are trying to take 3 reactants and hit them in space at the same time? No. I've got 2 bimolecular steps, so that also feels good. Okay? So you also want to check on that as you go through. What we noticed here, or what I noticed, and what I want you to notice, is that in this process, I wrote down NO3, and it dropped out. Okay? So NO3 doesn't even show up in the overall reaction, but it plays a really important role. And that role is our intermediate. All right? So an intermediate shows up, we generate it, and then consume it. So it was really important here. What is this whole process? We're waiting for NO2 to hit another NO2 to make an NO3. And then that NO3 is what reacts with the carbon monoxide. So it was very important mechanistically, but when you just see the overall reaction, it's not even there. Okay, so yet again, this balanced equation hides a lot from us if it's a multi-step mechanism. All right, so just make sure we have intermediates right in our mind. It's not a reactant, it's not a product, and it's not a transition state. It's this special spot right here, right? That's local minima. We want to say a couple more things about it. I thought I wanted to say a couple more things about it. Let's see, we know they appear along the reaction pathway. All right. And then I'll just repeat myself, that they're produced and then consumed. That order is important. We have to make them first and then use them. Catalysts are the exact opposite, so you got to make sure that you remember that we make these and then we're going to use them. All right. So let's go back to this rate law. All right, this reaction that we've been looking at. If we had predicted that it was an elementary step, we would have said, hey, it's NO2 times CO. But it wasn't. Experimentally, we found that it was NO2 squared. It was second order. We proposed this mechanism. This is a good mechanism because it sums to the overall reaction, and it's only bimolecular steps. So in that regard, it's good. Now we need to connect this mechanism to that rate law. Okay? All right, and now we have to consider how we do that. All right, how do we know? How do we determine, and the underlying question here is, how do we determine the rate law for a multi-step mechanism? And for that, we need to know this relative speed of our steps. Okay. And that's called, we want to find the rate determining step. And we'll look at, I think I've got an analogy on this one. All right. So, and walk with me here. We're doing an obstacle course. There's only 2 obstacles. One of them is this like incredibly challenging, like ninja warrior course thing or whatever. And then the next one is a toddler slide. All right. How fast I get through this obstacle course is entirely dictated by how long it takes me to do that first obstacle. Right? Like I'm going to need to take a couple years off from work and train. So like we're looking at probably like 2 years. And then this is going to take me less than a second. Right? So my overall time, how fast can I do this, depends on the rate determining step. All right? The same thing goes for chemical steps. How long it takes you to do it is going to depend on the one that's really slow. So I watch you guys get up every day at the end of class, and you guys stand up really quickly, right? And you could sit back down and stand up and sit back down, right? That's a quick step. And then you guys hit the bottleneck there, right? As you all slow down because you're all slowly leaving, because that is your rate determining step. How fast you get out of this classroom is not dictated by how fast you stand up. You can do that really quickly, nothing's stopping you. And then you hit that, and you're like, oh, how long it takes me is how long it takes me to get through this line, right? So that would be your rate determining step when you leave this classroom, all right? We want to find the similar thing. I want to be able to look at those 2 steps and say, hey, which one's fast and which one's slow? That's what we need to do. Because the slow one is going to tell us how fast the process goes, all right? So this is our big rule. Okay, if you take away nothing from this class, except for one thing, this is the sentence you should take. Okay, so if you are totally zoned out, come back. This is the important one. You have to write the rate law from the rate determining step. Okay? That is likely the step that has the largest activation energy. Okay? That's our slow step. All right? So we split these multi-step mechanisms into two camps. Okay? So mechanisms with a slow first step. Okay, that's one camp. Our second camp is a mechanism with a fast first step, which then means the slow step comes later. All right, so it's either the first step or it comes later. We're going to treat those two differently. Well, not really. We apply the same rules, but we can split them out this way. This should be the first question you ask yourself. Where does the slow step come? Is it first, or is it second or third? We're not going to give you anything more than that. All right, so let's go back. This reaction that we've been looking at for a while now, we find out that it's the first step that is the slow step. All right? Say, okay, that is my, like, the wall at the end of the Ninja Warrior obstacle course or whatever. Okay, this is the slow step. So what does this mean? Write the rate law from that step. What does that mean? You say, hey, I'm going to write it like that's the elementary step that matters. The rate equals K1, I'm just going to pull that number here, that specific K, times NO2 squared, because I have two NO2s there. So actually, this reaction, what it's waiting for is NO2 to hit itself. That's the slow thing. As soon as that happens, it's going to speed through the next step. But that's what I'm waiting for, which is why it has a rate law that is second order with respect to NO2, because that's what we're waiting to happen. Okay, we need that to happen, and it takes a while. Okay? So let's visualize this. Okay? This is our slow step. So I'm sitting here, I've got NO2 in my container. There's CO2 as well, but I don't care, because I can't react CO until I have NO3. So I have NO2 plus NO2, and I'm already regretting where I placed that on here, because I want it to be lower. All right, just draw it up high, okay? That first step has a big activation energy, okay? That's going to take a long time. That's what tells me it's slow, is because it has a big activation energy. Once that happens, okay, and I make NO3, and it's sitting there with NO as well, and my carbon dioxide, once I have this, it's like, oh, that's easy. And then we have a really small activation energy for the second step. As soon as the first step happens, that NO3 reacts with CO, and we get our products. We get NO2 and CO2. Okay, so that's our slow step. This is our fast step. How long it takes is just dependent on how long it takes me to get that NO2 to hit another NO2 to make NO3. And then it will go forward. All right? So here is a practice problem for you. The decomposition of nitrous oxide, N2O, is believed to occur by this two-step mechanism. I want you to write the overall reaction, identify the intermediate, and then write the expected rate law. Okay, take another about 30 seconds and then we'll do it together. Turn to someone next to you.
And then we did this at the end of last semester where you like cancel out to like extra.
Yes, it is. Yeah, no, it's similar to that. Yeah.
Okay. I was like,
all right, let's look at this together. I'm going to add these two equations together, these two reactions, and I'm going to knock out anything that shows up on both sides. All right, so I've got N2O twice plus this single oxygen atom, which seems suspiciously unstable. So I'm going to have 2 N2O plus O goes to, and now I've got N2. I've got 2 of those N2s. I've got that O again. And then I've got O2. And I'm just leave that. All right, so what can I cancel out? That oxygen cancels out. That's my overall reaction. My net reaction is that I have 2 N2Os decomposing to 2 N2 plus an O2. Because I canceled this out, we can double check it, but I made that O first, and then I consumed it in the next step. That's the definition of an intermediate. All right, so that would be my O, my intermediate there, that single atom of oxygen. And then the rate law. I'm not going to write it based off of my overall reaction. I'm going to write it based off of the slow step. Okay, so this is a first step, slow step. So just look at that, only that. And you say, the rate law is K1 times N2O. Okay, it's just first order. Right? If you look at the overall reaction, you might have looked at that and said, hey, it should be second order with respect to N2O because it's 2 N2O. But you're not, the first step is not waiting for those to hit each other. The first step and the slow step is waiting for one to spontaneously decompose. Right? That's what starts this off, is I have an N2O that decides it's going to be an N2 and an O. And that's the slow step. And that's how we write the rate law. All right? That's slow step first. And guess what? We're now going to do it when the slow step is not the first step. All right? So we have to consider this. When a mechanism doesn't have a slow first step, and it's a fast initial step. All right? Look at this. I think I have a question for you guys. The rate law for this reaction was experimentally found to be K times NO squared times Br2. Okay? So that's an overall third order reaction, right? Because I've got 2 plus 1. So overall third order. Well, let's write a 3. Third order. So is this a plausible mechanism for it? No, it's not. I cannot possibly conceive of 3 molecules coming together in the right orientation and hitting each other very often. Okay? So that's not it. When I see this high of an order, that also screams to me multi-step mechanism. Okay? Because this isn't it. This can't be a single elementary step. All right? So the following mechanism, which has only bimolecular steps, was proposed instead. Again, this is not something you need to generate, but you need to be able to write the rate law off of this. Okay? So we've got a fast step first where NO and Br2 make NOBr2, and then that reacts with the second molecule of NO. This is now a fast first step. Okay? Notice you should now be hopefully getting comfortable. Can you see the intermediate? Hold it in your mind. Have you identified it? We generate it, and then we consume it in the very next step. That NOBR2, that's our intermediate. Okay. All right. So we are still going to use, we want to now write our rate law, and we're going to use the same, the big red bolded statement. Use the slow step to write your rate law. We don't deviate from that. We do that. So we say, hey, there's our slow step. So the rate equals K2 times NOBR2 times NO. And then we stop ourselves and say, we don't actually like that. Using the concentration of an intermediate is dicey. Isn't great. Because that is really hard to monitor. We're probably not like generating a bunch of it. We don't know what it is because we didn't put it in. We didn't start with that. And so it's very hard to calculate a rate using an intermediate concentration. We would like to replace that. Okay? We want to replace that. Okay? So we're going to replace it. Redefine this NOBR2 with known values. Okay? Or known, let's be more specific, known concentrations. Okay. All right, so we'll do that. All right. So now I switch where I want to walk you through this mentally, and then we'll do the math. All right, now my second step is my slow step, okay? We can sit and jump this over and over again, right? This is like you all standing up and sitting down again, standing up and sitting down before you get out that door, okay? So this happens really quickly, which means we can assume equilibrium, okay? So this is like a preview into chapter 15, which is coming next. This first step is fast. It's fast, and I've written it as having a very small energy, activation energy. So it can go this way, and then, it's like, I'm sitting and I'm waiting for this second really hard step to happen. So maybe some of this actually goes back the other direction. And then we're just sitting over here, going back and forth, back and forth. So this is at equilibrium. Okay? Because this second step takes so long, it's so slow, that some of that NOBR2 is actually going to decompose and go back the other direction. Okay? So our definition of equilibrium, okay, we can write this mathematically, that the forward rate equals the reverse rate. And remember, these are elementary steps, so I can write that out. I can say that the concentration of NO, I'm doing forward first, okay? Just written it out like, hey, if this is an elementary step, I'm going to have a K times my concentration of reactants. And now my reverse rate is equal to K minus 1. Don't know how I did that. Oh, good for me. Cool. Don't do that. Oh, and now it just disappeared. It's like I've given up. You made one mistake, and we're done here. Ah. Okay, you guys can take this as a break time for a second. Okay. Sorry, guys. Psych. Short break time. All right, bring it back. Okay, so we said the forward rate. Does everyone feel comfortable with where I got the forward rate from? K1 times those two concentrations. But now I'm saying that the backwards process, the reverse process, can also happen. Okay, because this NOBR2 is sitting around waiting for this really slow, hard step to happen, it might decide to go back the other direction. So the reverse rate is K minus 1 times the concentration of NOBR2. That is the definition of equilibrium. That the forward rate equals the reverse rate, so that those aren't changing, okay? And now I can redefine that intermediate. So using this, I can say, hey, I could write NOBR2 concentration in terms of my initial reactants that I do know something about, because I did set up the reaction. So I know something about NO and BR2. So I'm going to have K1 divided by K minus 1 times NO BR2. And now I have a new definition that I can use, that I can plug into what we derived in the last slide. On the next one, we'll put it all together, okay? So we're going to grab this equation and bring it with us to the next slide, okay? So from the slow step, rewrote that the rate equals K2 times NOBR2 times NO, all right? And then using our equilibrium method from the last slide, we applied that to our fast step. Now we can say that the concentration of that intermediate is equal to K1 divided by K minus 1 times NO times BR2. And now I can take this and plug it in here. So my final rate law is K1, K2 divided by K minus 1, and we'll deal with that in a second. I've got two NOs, so that's going to give me my NO squared, BR2. There's my derived rate law when my second step is slow and my first step is fast. You will often see this. These are just 3 rate constants. They're just numbers. You will see them written like this. That is just some observed K value, and we don't care what it is particularly. We just want to know that it's there. Okay? So again, when you see a rate law where it's suggesting we have an order that is greater than 2, so I have an overall order of 3, that to me reads, not only is it multi-step, but it's probably a multi-step where the first step was fast. That's the only way I would get myself to a place that would make like a non-termolecular process. Okay, so when I see third order, 1, so third order, I'm going to say 1, it's a multi-step. Okay, it's got to be. 2, first step is not the slow step. Okay, that's what I would read out of that. Okay. All right. I'm going to throw you just into the deep end real quick. Here is another practice problem for you. So look through this. I have the overall reaction first. I say, hey, this is a proposed mechanism. The experimental rate law is there. Which step is faster? So now I'm asking you to assign which one is slow versus which one is fast. Okay? You'll do that because I gave you the experimental rate law. Then I want you to think about the relative size of those Ks. right. Here's how I would approach this one. I would make the assumption, I would guess and check it. I'd say, hey, if the first step were the slow step, what would my rate law be? Okay? And if I were to make that assumption and say, hey, if this were the slow step, right, then I would write the rate law just off of that, and I'd ignore this fast step that comes later. And when I do that, so assume first step is slow, I get this rate law, that the rate equals K1, or some K value, times ozone times nitrogen dioxide. And that is the experimental rate law. So I stop there and I say, hey, the first step was slow, okay? Because that gives me the right rate law. I could go through and assume the second step is slow and work my way back. What I'd find there is that we get a kind of a nasty rate law that would include 2 NO2s, and I'd also incorporate that O2, and that's not what we observed. Okay? So slow step has got to be the first step to be consistent with this experimental rate law. Okay, so that's our first answer. So which rate constant is larger? Okay, is K1 larger or is K2 larger? So give me sign of life, 1 or 2. Which one's bigger? Good. The faster step should have the bigger K. All right, so for this second question, K2 must be bigger than K1 because that was the fast step. And remember, a big K means a fast reaction. Okay? I could also extend that to say EA2, my second activation energy, must be smaller than my first activation energy, right? This is happening at the same temperature. It's all in the gas phase, so there's probably, unless there's some like weird collisional like orientation that's super different, A is probably similar. And so this all comes from the fact that my activation energy would be bigger for the first step versus the second step. All right, and then is there an intermediate? And hopefully you all said yes. And you said, hey, that NO3 pops up and then goes away. So my intermediate was NO3. Okay. All right. There is a multi-step mechanism question on the post-lecture practice exam quiz. So if you're like, I really need work on this, go to that. You've got a whole homework that is focused on multi-step mechanisms. So there's lots of practice for you before Friday. All right, I'm going to skip the next. I still have like a whopping 9 minutes, although you guys, I'm going to have you guys do this at home. That doesn't mean that we're done. It just means that I'm going to lecture at you for a little bit longer. So maybe take the cheer back. All right, so do that at home. I just want you to understand what these squiggles mean, all right? All right, so the very last bit of 14. You guys, we're here. This is the last content you need for Friday. You need to know about catalysts. You already know, because we've talked about it a couple times, catalysts speed up reactions, but you need to know how and why. All right, so a catalyst is a substance that changes the speed of a chemical reaction without undergoing a permanent chemical change itself. So I could write this a different way. Did I write that? No, I didn't. All right, a catalyst, okay, is consumed. So it's used, but then reproduced. So catalyst goes unchanged throughout the reaction, which means you can add a very little bit of catalyst and still have a huge impact because it is just continually regenerating. It catalyzes this reaction. like these two molecules, and then it finishes, goes over here and does it again. And it just keeps going and going. So you don't need very much of it. And it has an impact on the reaction because it provides a different pathway. It could be totally different mechanistically. It could be the same like pathway and just lower the activation energy. But at the end of the day, what we notice is that our products and reactants stay in the same spot, right? We're not doing anything, we're not changing anything about the beginning and end of this. Our blue line and our red line are in the same place. The only thing that changes is the pathway. And so we'll notice here that our uncatalyzed activation energy, right, is much bigger. Here's my, oh, and now I don't have it anymore. Is much bigger than either of the EAs that this reaction encounters on the catalyzed pathway. So that's EA2, and that's catalyzed. Here's EA1, and that's also catalyzed. And both of those are smaller. So even though this is a two-step mechanism, neither of those steps should take as long as our single step that's uncatalyzed, because both of those are small in comparison. All right? So our catalyst changes the pathway and makes it easier. And it's the opposite of an intermediate. It's consumed and then reproduced. Okay? All right. So I want you to look at this. The catalyst, again, is first consumed and then reproduced. An intermediate is produced and then consumed. I want you to write the net chemical reaction for these two steps and identify what species would be acting as the intermediate and as the catalyst. Okay, so we're getting better at adding these things together, and at the end of the day, this is a very simple net reaction. We're looking at the degradation or decomposition of hydrogen peroxide. So we have 2H2O2, and okay, degrading into water and oxygen. All right, that's our overall reaction. And all this other stuff has to be either catalysts or intermediates. Okay, so our catalysts are something that was there to begin with because we added it because we wanted it to do something for us. Okay, and then it is used and then reproduced. All right, so that's this Br minus and H plus. Okay, that was there to begin with. In the next step, it's gone. Right? We don't have it there anymore. We used it. We have different chemical species. Okay, so that bromide and that H plus is gone, but then by the last step, it's reappeared. So my catalyst species are the bromides and the H plus. My intermediate, the thing that I produced and then I consumed, right? That combines, I make this Br2. Okay, my bromine. And then in the very next step, I consume it, right? That's the definition of an intermediate. All right, so get comfortable identifying those. I have two more things to say to you, all right? You can confirm to yourself that quantitatively, the way that catalysts work, right? We are going to increase the rate. You put in a catalyst, that number goes up. It's obviously not changing anything about this part of the equation. What is it doing? It's making K bigger, right? And it's doing that by making this smaller. Catalysts make that smaller. So you can sit with a calculator and prove to yourself that that's true. And then the very last thing you need to know is that we classify catalysts into two different types. Okay? There's homogeneous catalysts, which exist in the same phase. I definitely have at least 1 more minute of your time. I have a generous 2 minutes, okay? So homogeneous catalysts are in the same phase. This is the reaction you guys just wrote out. That's our H2O2, and we're adding sodium bromide as our catalyst, okay? So we would define that as homogeneous because it's in the same phase, all right? Enzymes also fall into this category, okay? So enzymes are here. Or you could have a heterogeneous catalyst where they're in different phases. Here we have a sheet of metal. So this is what happens in your car, all right? Your car in your, why am I forgetting the name of it? It's the catalytic converter. Has a really nice piece of metal there. And things, other gases like to sit there. When they sit there, it lowers the energy and allows that bond to break, all right? That would be a heterogeneous catalyst. Those are the two things I need you to know. And now you have everything you need for your exam on Friday.